The general electronic configuration of group 1 elements is written as ns. This is one of the most important concepts in chemistry because it explains why all alkali metals have similar chemical properties. The expression ns is called the general electronic configuration because it represents the outermost electron arrangement of every group 1 element, regardless of how many total electrons the atom contains. Instead of writing the complete electronic configuration for each element individually, chemists use this short notation to describe the common pattern shared by all group 1 elements. To understand the meaning of ns, let us examine each symbol separately. The letter N represents the principal energy level, also called the shell number. The value of N changes depending on the position of the element in the periodic table. The letters represents the s orbital, which is the first type of orbital present in every energy level. The superscript 1 means there is one electron in that outermost s orbital. Therefore, S simply means that the outermost shell contains one electron in an s orbital. This single valence electron is the most important electron in the atom because it controls the chemical behavior of the element. The image explains the meaning of each part of Ns very clearly. It shows that N refers to the principal energy level or shell number. For example, N-1 means the first shell, N-2 means the second shell, N-3 means the third shell, and so on. As we move down group 1, the value of N increases because each new element has one additional electron shell. The letter S indicates that the outermost electron is located in the s orbital, and the superscript 1 indicates that only one electron occupies that outermost s orbital. Therefore, although the shell number changes from one element to another, every group 1 element always has one valence electron in an s orbital. The image also illustrates how the value of N changes for different group 1 elements. Lithium has the outer electronic configuration 2s, meaning its valence electron is located in the second energy level. Sodium has 3s, so its valence electron is in the third energy level. Potassium has 4s, rubidium has 5s, cesium has 6s, and francium has 7s. Notice that only the number before the letter S changes. The ending S remains exactly the same for every group 1 element. This is why the general electronic configuration of the entire group is written simply as ns. The complete electronic configurations of these elements make this pattern even clearer. Lithium has the configuration 1s 2s, sodium has 1s 2s 2p3s, potassium has 4s, rubidium has 5s, cesium has 6, and francium has 7s. Although the inner electrons differ greatly from one element to another, every configuration ends with s. Since the last electron always enters an s orbital, every one of these elements belongs to the s block. The atomic models shown on the right side of the image help explain why the value of N increases. Lithium contains 2 electron shells, sodium contains 3, potassium contains 4, rubidium contains 5, cesium contains 6, and francium contains 7. Every time we move one step downward in group 1, one new shell is added. Therefore, the principal energy level increases from 2 to 7. However, despite the increasing number of shells, the outermost shell always contains one valence electron. This is why all of these elements remain in the same group of the periodic table. The image also includes an important arrow labeled Increasing Principal Energy Level. This arrow shows that as we move downward through group 1, the principal energy level becomes larger because electrons occupy higher energy shells. Although the atoms become larger, their outermost electron still occupies an s orbital, so their general electronic configuration continues to be ns. The flow diagram at the bottom of the image explains how the electronic configuration determines the chemical behavior of group 1 elements. The process begins with a group 1 element, which has the general electronic configuration ns. Because it has one valence electron, the atom can easily lose that electron during a chemical reaction. After losing one electron, the atom becomes a positive ion carrying a +1 charge, represented as M, where M stands for any group 1 metal. This sequence explains why all alkali metals form +1 ions and exhibit very similar chemical properties. The reason group 1 elements lose their valence electron so easily is related to atomic structure. The single valence electron is located in the outermost shell, farthest from the nucleus. Between the nucleus and the valence electron are several inner electron shells that reduce the attractive force of the nucleus. This reduction in attraction is called the shielding effect. As the number of shells increases, shielding also increases, making it easier for the outermost electron to escape. Consequently, the electron can be removed with relatively little energy. The energy required to remove an electron from an atom is called ionization energy. Group 1 elements have relatively low first ionization energies because they contain only one outermost electron that is weakly attracted to the nucleus. As we move downward from lithium to francium, the distance between the nucleus and the valence electron becomes greater, and the shielding effect becomes stronger. Therefore, the first ionization energy decreases down the group, making the outermost electron even easier to remove. Because group 1 elements lose one electron so easily, they are among the most reactive metals in the periodic table. Lithium readily loses its single valence electron to form Li, sodium forms Na, potassium forms K, rubidium forms Arb, cesium forms Cs, and francium forms Foer. Every one of these ions has a +1 charge because exactly one electron is removed from the atom. This behavior is a direct consequence of the ns electronic configuration. Another important point is that although the inner electronic configurations become increasingly complex as we move down the group, chemists usually focus only on the outermost electrons, because these electrons participate in chemical reactions. The inner electrons remain tightly bound to the nucleus and usually do not affect ordinary chemical behavior. Therefore, the general electronic configuration ns provides all the information needed to understand the chemistry of group 1 elements. The expression general electronic configuration does not describe every electron in the atom. Instead, it describes only the common outermost electron arrangement shared by all members of a particular group. This is why lithium is written as 2s, sodium as 3s, potassium as 4s, rubidium as 5s, cesium as 6, and francium as 7s, but all are summarized by the single expression ns. This notation is extremely useful because it allows chemists to predict the properties of an element without memorizing every complete electronic configuration. Whenever an element has the general electronic configuration ns, we immediately know that it belongs to group 1, is an s-block element, contains one valence electron, easily loses that electron, forms an M ion, has relatively low ionization energy, and is highly reactive. The general electronic configuration of group 1 elements is ns, because the last electron always enters the outermost s orbital, and there is only one electron in that orbital. The value of n changes from one element to another as the number of electron shells increases, but the endings never changes. This common outer electronic configuration explains why all alkali metals belong to the s block, why they have one valence electron, why they readily lose that electron to form +1 ions, and why they exhibit similar chemical properties throughout the entire group. The general electronic configuration of group 2 elements is written as ns. This notation represents one of the most important concepts in the study of the periodic table because it explains why all alkaline earth metals have similar chemical properties. Instead of writing the complete electronic configuration of every group 2 element, chemists use the short notation ns to describe the common arrangement of the outermost electrons. This notation tells us that every group 2 element has 2 electrons in its outermost s orbital, and these 2 electrons are responsible for almost all of the physical and chemical properties of the group. To understand the meaning of Ns, let us examine each symbol separately. The letter N represents the principal energy level, also known as the shell number. Every electron in an atom belongs to a particular energy level, numbered 1, 2, 3, 4, 5, 6, and 7 as we move farther away from the nucleus. The value of N changes depending on the position of the element in the periodic table. The letters represents the s orbital, which is the first type of orbital found in every energy level. The superscript 2 indicates that 2 electrons occupy the outermost s orbital. Therefore, the expression N simply means that the outermost energy level contains 2 electrons in an s orbital. The image explains the meaning of each part of Ns very clearly. It shows that N stands for the principal energy level or shell number, S represents the s orbital, and the superscript 2 means that there are 2 valence electrons in the outermost shell. These 2 electrons are called valence electrons because they are located in the outermost energy level and participate directly in chemical reactions. The inner electrons remain close to the nucleus and usually do not take part in ordinary chemical bonding. The general electronic configuration Ns applies to every member of group 2, regardless of how many total electrons the atom contains. The value of N changes from one element to another, but the endings always remains the same. This common outer electronic arrangement is the reason why all group 2 elements show similar chemical behavior. The image provides several examples to demonstrate this pattern. Beryllium has the outer electronic configuration 2s, meaning its 2 valence electrons occupy the s orbital of the second energy level. Magnesium has 3s, showing that its 2 valence electrons occupy the s orbital of the third energy level. Calcium has 4s, while strontium has 5s. If we continue further down the group, barium has 6s, and radium has 7s. Although the principal energy level changes from 2 to 7, every element still ends with S. This is why all of these elements belong to group 2 of the S block. The atomic models shown on the right side of the image help us understand why the value of N increases. As we move downward through group 2, each new element contains one additional electron shell. Beryllium has 2 shells, magnesium has 3, calcium has 4, strontium has 5, barium has 6, and radium has 7. Therefore, the principal energy level increases from N²2 to N²7. Even though the atoms become larger, the outermost shell of every group 2 element always contains 2 electrons, so their general electronic configuration remains Ns. The upward arrow labeled increasing principal energy level in the image emphasizes this trend. It shows that as we move down the group, electrons occupy higher energy levels that are farther from the nucleus. The increasing distance between the nucleus and the outermost electrons makes the atoms larger, but it does not change the number of valence electrons. Every atom still contains 2 electrons in its outermost s orbital, so the general electronic configuration remains unchanged. The flow diagram at the bottom of the image explains how the electronic configuration determines the chemical behavior of group 2 elements. The sequence begins with a group 2 element, which has the general electronic configuration Ns. Because it has 2 valence electrons, the atom tends to lose both electrons during chemical reactions. After losing these 2 electrons, the atom becomes a positive ion carrying a +2 charge, represented as M, where M represents any group 2 metal. This simple sequence explains why all alkaline earth metals form +2 ions. The reason group 2 elements lose 2 electrons is related to the stability of atoms. Every atom naturally tries to achieve the stable electronic configuration of the nearest noble gas. When a group 2 atom loses its 2 outermost electrons, the next inner shell becomes the new outermost shell. This shell already contains a complete electron arrangement, making the atom much more stable. Therefore, losing 2 electrons is the easiest way for these atoms to achieve stability. Removing 2 electrons requires more energy than removing only 1 electron. This is why group 2 elements are generally less reactive than group 1 elements. Alkali metals have only 1 valence electron and need to remove only that single electron to become stable. In contrast, alkaline earth metals have 2 valence electrons, so they must remove both electrons before reaching a stable electronic configuration. Since removing 2 electrons requires more energy, group 2 elements react less vigorously than group 1 elements. The comparison shown in the lower left corner of the image illustrates this difference very well. Group 1 elements have the general electronic configuration ns, contain 1 valence electron, lose 1 electron during chemical reactions, and form M-ions. Group 2 elements, however, have the general electronic configuration ns, contain 2 valence electrons, lose 2 electrons during chemical reactions, and form M-ions. This difference of just 1 extra valence electron completely changes the chemistry of the 2 groups. Another important property explained by the ns configuration is the strength of metallic bonding. Since each group 2 atom contributes 2 valence electrons to the metallic structure instead of 1, the attraction between metal ions and free electrons is stronger. As a result, group 2 metals are generally harder, denser, and have higher melting and boiling points than group 1 metals. Stronger metallic bonds require more energy to break, making alkaline earth metals physically stronger than alkali metals. As we move down group 2, the atoms become larger because each element has 1 additional electron shell. The increasing number of inner shells creates a greater shielding effect, reducing the attraction between the nucleus and the outermost electrons. Consequently, the 2 valence electrons become easier to remove. This means that although group 2 elements are less reactive than group 1, their reactivity gradually increases down the group. Beryllium is the least reactive member, magnesium is more reactive, calcium reacts even more readily, followed by strontium, barium, and finally radium, which is expected to be the most reactive member of the group. The notation general electronic configuration does not describe every electron in the atom. Instead, it focuses only on the outermost electrons, because these electrons determine how atoms behave in chemical reactions. The inner electrons remain essentially unchanged during ordinary chemical processes. Therefore, writing S provides enough information to predict the chemical properties of every group 2 element without writing the complete electronic configuration. Whenever you see an electronic configuration ending in S, you can immediately recognize that the element belongs to group 2 of the S block. From this single notation, you can predict that the element has 2 valence electrons, forms an M-ion, exhibits metallic properties, has relatively low ionization energy compared with many other elements, and behaves chemically like the other alkaline earth metals. The general electronic configuration of group 2 elements is ns, because the last 2 electrons always occupy the outermost s orbital. The value of n changes as we move down the periodic table because each successive element has an additional energy level, but the endings never changes. This common electronic configuration explains why all alkaline earth metals belong to the S block, why they possess 2 valence electrons, why they lose 2 electrons to form M-ions, why they are less reactive than group 1 elements, and why they display similar chemical properties throughout the entire group. Understanding the meaning of Ns provides the foundation for understanding the chemistry of all group 2 elements.